of actually different subgroups. Okay, now, okay, let me just, let me rephrase that comment because it's, I don't want to confuse you. Let me just, say it like this. That the group of the set of matrices the set of matrices that form rotations in a given 2D plane have the form. So in some 2D plane, we have a rotation, say R, and we're rotating by some angle theta. And that matrix will have the form cosine of theta minus sine of theta, sine of theta, cosine of theta. Okay? And for infinitesimal theta, say delta theta, R of delta theta will be of the form of the two-dimensional identity matrix times delta theta times 0 minus 1, 1, 0. Okay, and this is the generator. So, R of theta form a group known as SO2, okay? So what I wanted to say is that, so these are orthogonal matrices, let me just use R, which satisfy this condition, okay? 2 by 2 matrices which satisfy this condition, so they're called SO2, as well as the determinant of R is +1, because there's an O2 as well, which includes reflection on a plane. So what we were calling Rx, is, belongs to a subgroup of SO3, belongs to a SO2 subgroup of SO3. Okay, and Ry belongs to a different SO2 subgroup of SO3, okay? And similarly, Rz also belongs to a different SO2 subgroup of SO3, okay? So at least intuitively, this should be clear. Is it clear? If so, why? If not, why not?
Sir, so what is really the notion of an SO2 subgroup of SO3? Right.
So SO2 it's basically a kind of a rank 2 by 2 matrix, which satisfy, group of rank 2 by 2 matrices, which satisfy, this thing. Okay, so so for example, these are the definition of SO2 matrices, right? So, and I'll set this as an exercise for you to verify that these are the SO2 matrices. So the fact is that if you look at the SO3 matrices, you see that there are like there are subgroups. So for example, if you take all the matrices of this form, nothing is interesting happening, in the planes which involve the X plane, right? All the action is, all the non-trivial action is happening in the YZ plane. And you see that this is just the R, what I was calling the R, the SO2 group. So there is a subgroup, SO2, hiding inside SO3. Is that clear, Nahi?
Yes, sir. I mean, like, it was intuitively clear, but the idea wasn't really concrete in my mind. Okay. So the other thing is that
similarly, you can see that this is also, these guys are also an SO2 subgroup, right? But you see that these matrices and these matrices do not commute. So they are different subgroups. Although they're both belong to subgroups SO2, they are different subgroups.
Sir,
and the two, yeah.
Would it be more correct to say that it has 3 subgroups that are isomorphic to SO2?
Yes, yes. But I just wanted to emphasize the fact that, okay, here also, see that, these guys, they form a subgroup as well. But what I want to emphasize is that these are, these are 3 different SO3s. From the point of embedding so there are different ways of embedding SO2 in SO3, and the rotations are on the x-axis, the y-axis, and the z-axis. These are 3 different embeddings. Okay, so this is okay. So this was SO3, SO2, and let me just give you an exercise about SO2. One of the things that, before I do that, one of the things that should be clear that, SO2 is an abelian group. Can somebody tell me why? What could be the reason?
Rotations don't matter, like how I rotate it, like if it's 60 degrees first, 30
in 2 dimensions, right? Yeah, in 2 dimensions, rotations commute, right? So that means that SO2 should be an abelian group. And you can also show that from the explicit form of this. So if you take 2 of these matrices, if you theta1, theta2, and you can just do a little bit of algebra, and you can show that it's
Sir,
commutes.
I had a question about the number of parameters. So
yeah,
to define a rotation in 2D, we just need 1 parameters.
Exactly.
But in 3D, it rises to 3 instead of 2, right?
Yeah, yeah.
So
you shall see,
like, yeah.
It's not the dimension of the space-time which determines the number of parameters, if that's what you're trying, yeah. So we'll see that when we have the group SON, that its dimension will be half n times n minus 1. Okay? So, hang on, did I? For n equals to, if SO3, then we get 3 times 2 times half, yeah, 3. And so that's for, yeah, and for SO, so this is for n equals to 3, right? For n equals to 2, we get 1, yes. So we'll see this, we'll derive these formulas, okay? Okay, So the exercise I want to give you is the following. To show that the 2 by 2, real matrices are, that satisfy R transpose of R equals to 1 form a group. Also, to show that determinant of R equals to +1 matrices form a subgroup which correspond to the elements which are continuously connected to the identity.